Hi everyone, we're doing Newton's laws in this chapter. In the last couple chapters we've talked about accelerated motion, but never saying why things accelerate. Now in chapter 4, Isaac Newton came along and gave us rules for why things accelerate. Like you see here, these planes. These planes are obviously either landing or taking off, so they're going from a state of rest to motion or from motion to rest, and what's going to cause that is an acceleration. Where do the accelerations come from? So that's what we're going to explore in here. Accelerations come from force. A couple forces we can deal with. We can deal with contact forces. Those are forces that you know of every single day that we use to move objects. Or there could be forces we call action at a distance force, where the force on one object interacts with the other object without any contact. So we'll go through a couple examples of what that means. In this section, what we're going to do is identify some forces and be able to show that the combination of all those, or superposition of all those forces acting on one object, can vector sum to what we call the net force, the total force acting on the object. So if you have 17 forces acting on one thing, the object will respond to wherever the total net force is. Kind of like displacements, kind of like we did with vectors where you added up vectors and saw what was left over. Same thing here with net force. Force is a vector, it's going to have a magnitude and direction, and you got to know both. There are four fundamental forces in nature. The one that we're always familiar with is the gravitational force that's acting on us at all times. The electromagnetic force, we're going to be getting into that a lot in the second half of this year. And the strong and weak nuclear forces that keep all atoms bound together so that they don't just blow apart. So let's go through those contact forces that we talked about earlier. There are 5 contact forces that we'll deal with. There can be many, many more, but really they're versions of what we have here. So the very first one on the list here is what we call a normal force, or the support force from a surface. A lot of times when people write F sub n, or sometimes you'll just see it written as just capital N. I'm going to demonstrate normal forces or support forces for you here with this demonstration. I've got a beam that's suspended across 2 tables, and to show you which direction the normal force points, I'm going to walk across this beam. So I've got my gravitational force pulling on me down at all points. That must mean that there must be a support force up on me. It's very hard to tell if this board is pushing up. The best thing I can do to show you that the beam is actually flexing when I go across and actually pushing back up on me is I have a laser set up in that top corner. It is shooting down onto the beam here, and with the fog machine going, what you should be able to see is that the beam is shooting straight down onto the piece of wood. It's hitting that mirror, and the dot up on the wall is showing the reflection of the beam from all the way over there down to the board and back up onto the wall. So to show that this board must flex, the beam would have to change points as I walk across the board. Pay attention to that dot in the top corner. What that demonstration is trying to show you there is that if here's the flat board and the laser is coming down and bouncing away, when I step on the board, even though the board may not look like it flexes much, you can tell that with a flex, that beam would still come down at the same angle, but now reflect at a steeper angle, cause that dot to move. So if the board is flexing down, the board does not like to be flexed, just like a spring doesn't like to be stretched, and it's going to try and return back to its original state. So here's no stress on the board, here's stress on the board. You can see that that board wants to flex back up to its original position. The normal force must push upwards at all times, or perpendicular to whatever the surface may be. Normal in math means 90 degrees. Perpendicular to the plane is showing us that we must flex back perpendicular to the stress that's put on it. So a weight on the board or someone pushing on a wall, every surface flexes even though you can't see it, and that flex pushes back, and that's what we call a normal force or a support force. There's frictional forces. Abbreviate that as little f or big F, little f. For me, I usually end up writing it just as little f for the force of friction, and it's the force that opposes when things slide across surfaces. Chapter 5 will deal with the force of friction. Spring forces are when you take a spring and stretch it or compress it, depending on what the spring lets you do, and there is this internal fight that when you pull the spring and it doesn't like to be stretched, it wants to pull itself back and bring it back to its relaxed length. So that would be the example of a spring force. Strings or ropes have what we call tension in them. We use the variable T for the force in a string or its tension. One thing you can never do with a rope, you can never push on it. Try it. Try tying something up and push with your rope. Ropes can only pull. And the last thing there are applied force. I just have the label F there, but you could call it force applied, F-A-P-P, a force that someone or some object puts on something else that doesn't fall into a string or a spring category. Springs and strings you may even call tension in springs a tension force, a frictional force, or a support force. That's another way of thinking of normal force. We've got 5 forces that basically you can run through every single time you see a scenario and see if any of these forces are interacting with the object. Example here is the wall supporting that ladder, pushing the ladder in the direction that it's trying to move. A frictional force here, as he tries to push the block in one direction, the frictional force acts in the complete opposite direction. And another example here is a spring force. The spring force can pull an object. If you look at that first example, the spring is relaxed. It does not feel any tension or compression. But in B, you pull it too far to the right, so it wants to accelerate or back to that center point. And if you push it too far in the other direction, you can see that that spring force now tries to push it back to that start point. So spring forces react in the opposite direction of which way they are stretched. A big thing that comes up a lot is this distinction between mass and weight. And mass and weight are not the same thing. Another way of saying weight is your gravitational force. We said that there are 5 contact forces. Gravitational force is this force that acts on you without having to touch you. Gravitational force is how gravity interacts with your mass and tries to accelerate your mass back towards its surface. All objects on Earth feel a gravitational field strength from Earth, and that gravitational field strength will cause you to accelerate. Gravitational fields always pull inwards, so no matter where you are on the planet, you're always being drawn inwards towards the center of the planet. The distinction between weight and mass: weight is just the force of gravity, how strong gravity pulls on your mass, and your mass is just the amount of matter that makes up your body. It's the amount of kilograms, how many atoms actually make up your body. And it's another way of thinking of mass is a way to measure your body's inertia. So we will do some demonstrations in class with inertia. Without even weighing things, you'll be able to tell which one's more massive just based on whether the object wants to stay at rest or whether the object wants to stay in motion. The base unit for our mass is going to be in kilograms. The whole goal in this section is to look at an object Identify all the forces acting on the object, and then determine the net force, the total resulting force on the object. What we'll do here is we'll say have the last 5 brownies your mother made. On the left side of your screen, what I'm going to have is the individual forces acting on each brownie, and on the right side of the screen, I'm going to have your total net force this brownie would feel. So let's say that in the first example, that 15 pounds. And at the same time, your brother or sister grabs onto that brownie and pulls the same way with a force of 5 pounds. Question over here on the right side is, what is the total net force? Well, since those vectors are in the same plane, just like with displacements or velocities, we can add them and we get a resultant net force to the right here of 20 pounds. Simple vector addition. We can reverse that. We could say, hey, you pull one way because you really want the brownie, 15 pounds to the left, and your sibling pulls 5 pounds to the right. This is the typical scenario that happens when there's one more brownie left. The net result of this is a total force to the left this time, negative 10 pounds. Or you could say 10 pounds to the left as long as you throw a direction on there. Forces are vectors, so it has to be there. Let's say not just 2 people are fighting over this. We've got 3 people pulling to the right, along with 2 people pulling to the left. In this scenario, let's say that these 2 forces are equal, and they're 20 pounds each. This force looks a little weaker, so it's about 15 pounds. Over here, these look even at around 12 pounds. 5 forces acting on the brownie. The question is, where is the net force? Where does this brownie feel like it needs to go, where it needs to accelerate? So if you look at everything on the right, you've got 20, 20, and 15. So you've got 55 pounds to the right, and you've got 12 and 12 to the left. That's 24 to the left. So 55 minus 24 ends up giving you 31 pounds, but which way? 31 pounds to the right. So the 3 people on the right are the people that end up eating that brownie. Let's say you've got 1 person pulling to the right. Let's go with 17, just to make the numbers a little different. And the second person comes along, but they're at right angles to you in the dining room table. They're pulling upwards at 8 pounds. Where in the world is this going to go? Just because forces are not in the same plane doesn't mean we can't add or subtract those. We can just add them tail to tip. 17 up to the right, 8 pounds up, gives us a net resultant force off to the right. I'll let you work that out. Tell me what that resultant force of these 2 forces, right angles, is, and tell me the angle. What direction would that brownie leave in? And one last example, we could have forces in all 4 directions. Multiple down forces, a force to the left, a force to the right, heck, even a force at an angle. And just like before, you want to break all your forces into X and Y pieces. For this angled force, I've got an X component and a Y component. So it looks like I have 2 up components, 2 down components, 1 left component, 2 right components. And if all those components were even, I would give you that the answer is net force to the right of whatever that value is. It can be many, many forces acting on an object. The overall net force is going to drive and accelerate the object in a particular direction.